Okay, so welcome back, everybody. Thanks for being here for the last session of invited talks of the on equilibrium statistical mechanics. So the first speaker today will be Federico Camilla, and so please come. Federico, you will also receive this nice medal as an invited speaker. And Federico will present his results on scaling behavior and decay of correlations in the near-critical planar Ising model with an external field. So, please.
Let me see. Go back to. Should I? Okay. All right. So let me first thank the organizers, Alessandro and Ivan, for organizing this session and for inviting me. It's a pleasure to be here, especially to be able to give a talk in front of a live audience, in front of people rather than in front of a screen. So my talk today will be about some aspects of the critical and near-critical scaling limit of the planar Ising model. And let me try not to play. Okay. So I believe that it's based actually on joint work with a number of different people, but mainly the main result I'll be focusing on is based on a recent paper with Jianping Zhang and Chuck Newman. I believe that in front of this audience, it's not really necessary to explain why the Ising model is important. It's not moving anymore. Sorry, having some technical issues. Okay. Is there? Okay. But let me just say a few words. So the Ising model is a paradigm for the study, of continuous phase transitions and critical phenomena. And in fact, it has played a really crucial role in the development of statistical mechanics in general, and more specifically in the study of critical phenomena. In particular, it helped elucidate some very important key features in the theory, such as power law versus exponential decay of correlations, the scaling behavior at the critical point or near the critical point, the behavior of the correlation length as you approach the critical point, and more generally, the link between critical phenomena and quantum field theory. All of these aspects, in one way or another, have been in some ways mentioned at this conference. The Ising model has come up, not surprisingly, several times. It's one of the most studied models of statistical mechanics. And there has been for quite a while a very good, I would say, understanding, let me say, within the physics community of the features that I mentioned here. But in some sense, from a mathematical point of view, one could say that there's no, these features are not completely fully understood. If by that I mean, by fully I mean in a complete and mathematically rigorous sense, not even in the restricted setup of the Ising model, at least not until recently. And in fact, I want to discuss a recent project that in some sense I think closes the gap, at least mostly, in the context of the Ising model. So let me introduce the model. Again, I suspect many of you are familiar with the model, but at least it can be useful to set the notation. I will, for specificity, consider the Ising model on the square lattice. So I start with actually a scaled version of the square lattice with a lattice spacing A. And to start with, you can consider a finite domain within your lattice. And I'm interested in looking at what are called spin configurations, which are assignments or a +1 or -1 to each vertex of the domain lambda. On this space of configurations, I want to put a probability measure. So I do that in a Gibbs measure. I do that in the usual way, starting with a Hamiltonian. It's a function on the configuration space. It contains two parts. So here, one part is a sum over all nearest neighbor vertices of the products of these sigma or spin variables. And then there is a second part which is proportional to the sum over of all the spin variables. And the proportionality constant is to be interpreted as an external magnetic field. Let me remind you that the model itself was introduced as a model to study ferromagnetism. So once I have this energy function, I use it to build a Boltzmann-Gibbs distribution in the usual way. So there's a Boltzmann factor, and there is a partition function, and there is a parameter beta, which is positive. It has to be interpreted as an inverse temperature. The model is interesting because it undergoes a phase transition, and there is a critical value of the parameter. I wrote down the numerical value here for concreteness, but it doesn't matter for this talk. But the behavior of the model is very different for values above or below this critical value and at the critical value itself. But one thing that is known, has been known for a long time, for beta less and beta critical, there is a unique infinite volume limit. So we'll be considering this infinite volume limit. Lambda tends to the full lattice. And eventually, the reason I made the lattice spacing explicit is because I'll be interested in scaling limits, which means I want to let the lattice spacing A, I want to send it to 0. So very briefly, a few milestones, and this list is very partial and sort of subjective, but these are results that are in some way relevant to this talk. The model itself was introduced by Lenz, who gave it to his graduate student Ising to study. It picked up, interest in the model picked up in the 1930s and 60s when Pliers showed that the model undergoes a phase transition in 2 dimensions. Onsager solved found the free energy for the 0 field case, again in 2 dimensions. Later on in 66, Wu proved that at the critical point means for the critical value of beta, and this will be fixed for the rest of the talk, and with 0 external field, the 2-point spin-spin correlation decays as a power law, and that's one of the classical power laws in statistical mechanics with exponent 1/4. All of these results are for 0 external field. The model with an external field is still intractable in a sense. There's no solution, at least not on the lattice. But in some sense, in '89, Homological provided some sort of a solution. I'll come back to that later, directly in the scaling limit. This is not a rigorous result, and I'll say a little bit more about that later on. A great breakthrough happened in 2010, or shortly before that. 2010 is the year when the paper was published, when Stas-Smirnov proved conformal invariance. So this is an idea that goes back to the 70s and 80s with Polyakov and co-authors. The idea that if you take a model of statistical mechanics at the critical point, in the scaling limit, you get additional symmetries, and in particular, the model becomes invariant on a conformal, the full set of conformal transformations. And this is very powerful because that's a very big restriction, especially in 2 dimensions. But until Smirnov's paper, this wasn't proved rigorously. So building on that, a few years later, Chelka, Hongler, and Zurov proved conformal invariance of the endpoint functions. Again, at the critical point, you can think of that as a vast generalization of Wu's result. And around the same time, Chuck Newman, Christoph Garban, and I were working on the scaling limit of the magnetization field, which I'll mention in the next, I'll introduce in the next slide, at the critical point and in the vicinity in the so-called neocritical regime. And I'll mention these results again. I'll discuss them a little bit, and then I'll move on to the next result, which was only published last year, which sort of completes the picture, proving that the neocritical scaling limit is a field that has exponential decay of correlations. Okay, so going back to the easy model on a lattice, think of a bounded domain and its intersection with the scale version of Z2 that gives you your finite domain lambda. The magnetization, so for each vertex you have a spin variable, which takes only 2 values, +1 or -1. We have inverse temperature, which is fixed. It's the critical one. The magnetization is the sum of all the spins within any region of space. Defined in this way, it is a random variable, but it's actually convenient to think of it as a measure, because then you can take weak limits. So think of taking an infinite volume or thermodynamic limit, and I would like to define a magnetization as a, let me call it magnetization field. As written there, this phi which depends on the two parameters in this, the lattice spacing and the external field. It's a sum of delta functions, so to each vertex of my scaled version of Z2, I attach a Dirac delta function multiplied by the corresponding spin, and I take the sum of all of those, so I have a signed measure. And eventually, as I said, I want to take scaling limits, so I want to let the lattice spacing go to 0. And in order to do that, it turns out I have to rescale this quantity, and I have to do it appropriately if I want to obtain a meaningful limit. It turns out that appropriately in this case means the lattice spacing to a specific power, which turns out to be 15/8. I don't have time to explain exactly why that is the case, but you can think of it as 2 minus 1/8. 2 is the space dimensionality, the dimension of space. We are in 2 dimensions. And 1/8 is the so-called scaling or a conformal dimension of the spin field. And it's closely related to the 1,4 in Wu's law, which I showed in the previous slide. Now, once you you define the magnetization, or you think of the magnetization in that way, let me point out that in the Ising model, as I said, it was introduced as a model to study ferromagnetism and to try to model the ferromagnetic phase transition, which actually works in 2 dimensions or higher. There are 2 main quantities of interest. One is the energy, the other is the magnetization. We're focusing here on the magnetization. Now, physics wisdom tells us that if you take a scaling limit of this object at the critical point, so beta critical and h equals 0, you're supposed to obtain a field that is conformally invariant under conformal transformations. And I'll explain in the next slide a little bit more what I mean by that. The physics wisdom also tells us that if you have an external field and you send it to 0 together with the lattice spacing in an appropriate way, and I'll say what appropriate means, you're supposed to get a different field. You're supposed to get a meaningful limit, but that is different than the limit you get at 0 external field in the sense that you expect to have exponential decay of correlations for your field. And the terminology that is used in this case, which is borrowed from quantum field theory, is to say that the field is massive. Okay, so the point 1 was covered with, in fact, relatively recent results published in 2015, as I said, with Chuck Newman and Christophe Garban. We showed that indeed at the critical point, so beta critical 0 external field, you have a limit in distribution, and the field converges to a conformal field it's not a function, and this was also to be expected. It's a generalized function or a distribution, if you want. And it's conformal in the following way. So we have this let me try to explain what that equation means. I don't know if I can point to it. So that equation, which I put in quotation marks for at least 2 different reasons. One is that it can only hold in distribution, but more importantly, the field itself, as I just said, is not a function, so it cannot be computed pointwise. So this is only a formal expression. But if you take it at face value, it tells you something. So if F is a conformal map, you can think of a conformal map as a combination of a translation, rotation, and scale transformation and dilation. And the amount of dilation pointwise is given precisely by the modulus of the derivative of the map. So this equation tells you that the field phi, or phi 0, is invariant under translations and rotations, and only is only affected by dilations, and it transforms in a very simple way, where you see again this exponent 1/8 appearing in that expression. Okay, so that's what we mean by saying that the field in the scaling limit is conformally invariant or covariant. So that gives a complete proof and understanding of this feature in this case. So again, with Christophe and Chuck, we also studied the neocritical scaling limit, which means introducing an external field, which is then have to send to 0 in a very specific way, namely, as shown here, it should be proportional to the lattice spacing to the power 15/8. Again, this sort of magic exponent. And when you do that, you can show, we could show that you get a different limit. It's again a generalized function. It's again a distribution, so it's not defined pointwise. It has similar properties under conformal maps. So you see, if I, in this case, let's apply just a simple dilation by a factor of lambda of space. You see this lambda to the -1/8 is the derivative of the map. But in this case, you have a non-zero external field, so that needs to be adjusted. Of course, this equation is consistent with the previous one with when little h is equal to 0. So this gives you a pretty good picture of what you get in the scaling limit, what type of fields. There was one feature that was missing, which is important, and I'll explain why. And that's the main result I want to discuss in this talk. At the time, we couldn't prove that the field is massive. As I said earlier in the previous slide, that's language borrowed from quantum field theory. In this context, it means showing that the correlations decay exponentially. Okay, so this was actually done more recently in a paper that appeared last year together with Jianping Zhang and Chuck Newman. And the main result of the paper is a bound on the decay of the truncated two-point function. So the truncated two-point function is a classical object in statistical mechanics. It's the two-point function minus the product of the expectations of the spins. And this result may seem to experts somewhat surprising. Why should I make such, I mean, in the sense that exponential decay for the Ising model with an external field was proved a long time ago. It's a classical result. But this result is really tailored to the neocritical regime, meaning that we are assuming to be at the critical temperature and to have a specific external field which goes to 0. So we're interested in taking scaling limits, in fact. So we take an external field that is proportional to this power of the lattice spacing, 15/8. And it's a result that is much more precise than any previous result on exponential decay. Existing results could not be used to take scaling limits. And let me explain why. So let me tell you what is special about this result and what makes it so useful. It's mainly two features. One is that, as you can see from the upper bound, there is a sort of corresponding lower bound that I won't discuss for lack of time, but let me focus on the upper bound. It has one important feature is that it contains two parts. It contains together the power law decay, which is the dominant behavior for short distances. It's the remnant of criticality, if you want, together with the exponential decay. So it combines these two decays, together in one upper bound, and that's extremely important. And the other thing is that the rate of exponential decay is exactly what turns out to be the correct rate. That means the dependence of the external field is exactly the correct dependence, with, again, this exponent that keeps popping up, 8/15 or 15/8. Okay, so these two features were not present in any other previous result and are extremely important. In fact, they are necessary if you want to be able to take a scaling limit. So once you have this, and almost all of the paper is dedicated to proving this very precise exponential decay type of bound, which is very tailored to this neocritical situation. Once you have this, you can immediately basically go to the scaling limit. Go to the scaling limit implies that you need to sort of normalize the truncated two-point function. You do that by multiplying by the lattice spacing to the power -1/4. This you know a priori because you know it from Wu's result. The fact that the criticality of the two-point function decays as a power law with exponent 1/4 means that if you want to take a scaling limit at criticality or near the critical point, you have to normalize your two-point functions or truncated two-point functions by the lattice spacing to the power -1/4. And then you see why it's crucial to have this power law part here, because this a to the 1/4 kills the a to the -1/4 that you need to use as your renormalization in taking a scaling limit. And then here you see that the lattice spacing disappears already, so you can immediately and without any problems take a scaling limit. So these two features are extremely important. In fact, they are necessary. And once you have those, you immediately get a result for the limiting field once you know it exists. And you should remember that the field is defined as a distribution, as a generalized function. So if I have two functions, f and g, say C infinity with bounded support, when I apply the field phi to f and to g, I get two random variables, and their covariance now has an upper bound, which has, again, these two features. There is the power law decay, which dominates at short distances, and is what is left is the remnant of criticality, and then there is the exponential decay with the correct power in terms of this small h, which is a sort of renormalized external field. If you compare, so this is another way of writing, a formal way of writing the previous equation. If you compare this behavior with the expected behavior, which tells you that the system near criticality has a certain characteristic length, it tells you that the characteristic length, also called correlation length, in fact has a power law and diverges precisely as a power law in terms of the renormalized external field small h. So this concludes, shows the emergence of this power law. Now, let me go back very quickly to Homologikov's result. This is something that I will just mention very briefly. For those who were here at the previous session, you can think of Gubinelli's talk. There is a relation between Euclidean fields that are obtained by taking scaling limits of models of statistical mechanics at the critical point in quantum field theory. A lot of people have worked on that in the 70s and 80s. There's a long list of names. It starts with Szymanczyk, Nelson, Whiteman, Gliman Jaffe, and others. Essentially, in the two-dimensional case, you can think of one dimension as space and the other dimension as time, or imaginary time. And by performing what is called a weak rotation, or using results of Osterwalder-Schrader, you get a correspondence between Euclidean fields and quantum fields. And in that correspondence, the correlation length becomes the mass gap, or is related to the mass gap. In fact, it's the inverse of the mass gap. And it's in this setup, in this context, that Homologikov solved the quantum field theory, non-rigorous, as I said, but found a very interesting theory which seems which contains 8 different masses, and the mass spectrum seems to be related to the exceptional Lie algebra E8, which makes this whole theory very interesting and intriguing. So in this context, our previous results say that if you look at the corresponding quantum field theory, it has a mass gap, and it gives actually it gives you a power law of the mass. Tells you what the mass gap is in terms of this renormalized external field, and you have a precise power law. We can't compute the constant, but it's an exact power law. So you can think of this work, if you want, as a culmination of many years of work, and at the end of a line that was an attempt to rigorously prove all of these features that should be there in the Ising model. But you can also think of this as the beginning of a new line of research which aims at trying to validate or prove Homologikov's theory. And in some sense, you can think of this, since the mass gap corresponds to the smallest mass in Homologikov's theory, you can think of this as a proof of the fact that the theory is massive. There is at least one mass. And so this is a very first step in that direction. If you want to know more about other masses, what about, can we go beyond M1? The first one, at this point, I can't say much. You may want to take a look at this paper, recent paper, which contains some ideas. And I will just briefly end just with a list of tools that were used. The proofs used a number of different tools, some of them very classical, like the FK representation of the Ising model, the Edwards-Sokal coupling. Since we're dealing with an Ising model with an external field, and I'm saying this only for the experts, we need the version of the FK of the Edwards-Sokal coupling with a ghost spin. But in fact, we have to twist it and use a surprisingly new version that hasn't been used before, in which it's not individual vertices that are connected to the ghost spin, but entire FK clusters. And that is very important when you want to take a scaling limit, because in the scaling limit, the lattice spacing goes to 0. Individual vertices don't really make any sense in the limit, continuum limit, but the clusters, the FK clusters, a criticality, they do have a limit in some sense. But we also use more recent tools like conformal loop ensembles and conformal measure ensembles. Many of you probably have heard about conformal loop ensembles. I don't think many of you have heard about conformal measure ensembles. That's a tool that was actually designed to tackle this problem. Conformal loop ensembles were, the first conformal loop ensemble was actually introduced in the context of percolation in a paper by Chuck Newman and myself, where we constructed the full scaling limit of percolation, but the general concept was introduced by Sheffield, and then the theory was developed by Sheffield and Werner, and various other people, including Kempinen and Smirnov, in the context of FK percolation, which is relevant here. Conformal measure ensembles, as I said, is a more recent concept that was really designed. You can think of it as a collection of conformally covariant measures, if you want. And just very briefly, I want to mention at the end a preprint that I came across recently, which actually provides a new proof of some of the results I discussed. And I mention it, I find it interesting because it uses different methods, namely the random current representation for the Ising model. So that provides an additional tool, and that's something I think is interesting. And I stop here. Thank you.
Thank you very much, Federico, for this nice talk. Are there questions? Yes, please.
Thanks a lot for a very nice talk, nice paper. I wonder if this, I've asked myself this question for many years, and that is the particles that Homological speaks about. Do they have any form of, can we see them in the usual Ising model in some way, or does it even make sense to ask this question?
Yeah, so the first one, the smallest mass, has a clear meaning when you look at the spectrum of the, again, so if you look at it, if you think of it in this context, you can associate to your conformal, to your Euclidean conformal field, you can associate a quantum field theory. There is a this is, we know how to do that. There's a clear recipe for doing that. And the smallest mass has which is the mass gap in the energy momentum spectrum of the quantum field theory, has a clear meaning, and that's the rate of exponential decay. For the other ones, it's not so clear, and that's what makes it harder to get them. Like I said, you can, if you look at this paper, maybe we can discuss later. If you look at this paper, there are some ideas of how you might move on to the next mass, maybe the third one. We have some conjectures, but in general, my answer is at least I do not know of a simple way, and that's what makes it so hard. It's not something that you see very clearly in the spectrum, for example. You can't say there's another gap in the spectrum and that's in the next mass. It gets more complicated than that.
And is there even supposed to be a way?
Well, there is. I mean, there is a way. The way is to the straightforward way, which I think is difficult, and I don't know how to do that. Is to, if you could study more, you really have to look at the energy momentum operator in the quantum field theory and study its spectrum. I don't know how to do that, and I don't know, especially I don't know how to do that from the statistical mechanics point of view.
Are there other questions or comments? Yes?
Yeah, so how far are your methods from working for general FK, so Q not equal to 2?
Okay, so that's an interesting question. Some of the tools, so there is in some of the tools we think should be applicable to other models. For example, this conformal the concept of conformal measure ensemble, which there's a paper I mentioned here, was developed in this paper for FK percolation with Q equals 2, the Ising FK percolation, and for Bernoulli percolation. The concept itself, I think, could be generalized to Potts models and even beyond 3 dimensions. Some of the methods are actually potentially more general, but what we do need, at least what we do use, is the existence of a CLE. And for that, so we know that there is a scaling limit in the case of Ising FK percolation. We know that it leads to CLE, and we use the properties of CLE. If you could do that for other models, then in principle, I think you could use at least some of the methods we use to get similar results for other models. But that's the starting point. So the conformal invariance and the existence of a scaling limit for the boundaries of clusters, FK clusters.
So very quick follow-up. Does that mean you believe, so should the result not hold for Q bigger than 4, but an external field?
No, certainly not the methods. So for example, as I said, I think you can, these conformal loop ensembles make sense. The conformal measure ensembles make sense for the Potts model, but for Q below 4, not above. And they also, it should make sense also, say, for the Ising model in 3 dimensions. I'm not sure about 4, but in dimension larger than 4, it shouldn't really make sense. And it's related to the fact that you expect a Gaussian limit, or you know that there is a Gaussian limit.
So you formulated your theorems as upper bounds on the correlation function. Are there corresponding lower bounds, or is there no point in having them?
Yes, no. As I mentioned it, but too briefly, I only talked about the upper bounds, but there are corresponding lower bounds. And the corresponding lower bounds, it's interesting. We proved them in the original paper using reflection positivity methods. In a follow-up paper, we proved the lower bounds using purely probabilistic methods, so you can do it in 2 different ways. But you do need lower bounds if you want to, if you want to get this result, and if you want to prove this, you do need also bounds in the other direction, yes.
Thank you.
I don't see online questions, so I think we can thank the speaker again. Thank you, Federico. And we can move to the next speaker, Julian Dubeda, who is online. Before he starts, a brief introduction. Julian Dubeda obtained his PhD in 2004 under the supervision of Wendelin Werner in Paris Sud. Later, he moved to the US, to Columbia University in New York, where he is now associate professor. Julien Dubeda obtained several remarkable results on Ising models, dimer models, Liouville quantum gravity models based on methods of stochastic geometry, SLE, discrete and continuous conformal symmetry. And today he will present his talk on deformation perspective on Liouville CFT. So please.
Thank you for the kind introduction. So is it sound good? Okay. So what I want to discuss today is joint work with Guillaume Rémy, also at Columbia, on a more somewhat complex geometric approach to what you get for CFTs in the limit. So if somehow you manage to take a limit, what's somehow the both complex geometric and algebraic structure you're supposed to see, and make connection with classical approaches from the 80s in CFT. So maybe I'm going to again be a bit short on the background, since it's a very distinguished.
Julien, can you put full screen, please? Would be.
Yeah, not really. No. So Yeah, I
No,
don't think
okay.
you see it. You know, because I want to make also a notation.
Okay,
and so on,
no
so-
problem.
right.
Thanks.
Okay, so right, so well, okay, so again, so as you know, Federico just discussed Ising, which is somehow a good thing to have in mind. So if you have a model, at criticality into dimension, what you expect is if you manage to take a scaling limit, well, if you manage to take a scaling limit, what you get is a continuous limit has to be scale invariant. If you have something which is somehow universal scaling limit, in particular, it has to be invariant under rotation, first of the lattice and then like general rotation of the plane. And if you also have decay of correlation, then you should get invariance under anything which is to first order composition of a rotation and a dilation. And these guys are conformal maps. So that's, in general dimension. In 2-dimension, what's of course particular is you have a lot of conformal maps. You have somehow an infinite dimensional of, at least formal group of conformal maps. And in the continuum, there's a nice somehow testing ground for these ideas, which has been developed, in particular in these recent years, which is given by Liouville Cfts, which I'm going to discuss. And these are somehow based on the Gaussian free field. So you're somehow already in the continuum, but the general structure and feature is what you would expect from something coming from a combinatorial model such as, let's say, Ising or free pods. Okay, so I'm going, so maybe, everybody is like very familiar with statistical mechanics, but maybe not so familiar with complex geometry. So, so maybe I'm going to discuss that a bit more. So classical, classical object to look at in complex geometry is a space of equivalence classes of Riemann surfaces. So let's say you take 2 Riemann surfaces of a given genus, and then maybe you're going to look at correlators. So for correlation, you're going to mark points. So you're going to have some Riemann surfaces with additional structure, which are such as this, and then they are equivalent if you have a conformal equivalence between these two guys. They are the same, object in the category of Riemann surfaces. And you look at the space of equivalence classes. So very classically, if you look at tori, what you get is a modular curve. So each complex torus you can identify with a standard torus, which looks like that. So you can identify a complex torus with marking, which is given by these two cycles, with an element tau, which is a point in the upper half plane. So the space, something which is kind of not obvious, is that the space of these equivalence classes has itself a natural structure as a complex manifold. So space of equivalence classes of complex manifold is itself a complex manifold. So in that case, it's somewhat trivial because tau is already given naturally as a complex number, but that's a general fact. And there are very classical ways to go about, and different equivalent ways to go about doing this. And classically, you see it often done by the Beltrami equation, and using the approach of quasi-conformal maps. So I'm going to discuss another also a classical description, which goes back to Kodaya and Spencer, which, as it turns out, it's quite well suited to what we're going to do. So, so again, so this cursive T is my space of equivalence classes of maps, and I'm looking at its tangent space. So I'm trying to describe the space of all Riemann surfaces of this type, of equivalence classes of Riemann surfaces of this type, which are very close to my initial Riemann surface, so the tangent space. So one way to do it is, so very geometric operation is I'm going to mark a small neighborhood here, this small disk, and I'm going to make perturbation in this disk. So I'm going to make a local perturbation of the structure, and the perturbation goes as follows. So I'm going to change the gluing data. So if you look back at like very classical or like very basic definition of Riemann surfaces, so Riemann surface is something you can get by patching complex disks. So you patch, you have an atlas of complex disks, of like usual disks. And then you have some patching data, and the patching data has to be biolomorphic in the overlap. So I'm pulling out this small local neighborhood. I'm going to patch it back, but when I patch it back, I'm going to slightly deform the patching information. So I'm going to deform this patching information with a Laurent series. So I only need to do this patching in an annulus because I have a cover with a small disk and everything else. I'm going to change the patching data, and I'm going to change it by something which is biolomorphic in an annulus. And we know that something which is, something in that case, which is an holomorphic vector field in an annulus, I can represent by a Laurent series. So summing from negative infinity to plus infinity. So that's sometimes referred to as a Virasoro uniformization, because it's going to connect like very quickly to representation theory. So again, so I got this Laurent vector field. So I've got, again, so the picture is that I've got this small annulus somewhere in my, so I've got a point of interest around which I'm making the deformation. I'm taking a small annulus around this point. And in this small annulus, I'm going to slightly deform the patching data by this Laurent vector field. This path of Laurent vector field has a natural basis given by monomials. Everything is written in the local coordinates, so that's going to be important. So everything is relative to a choice of local coordinates. And this basis of monomial, as is well known, as you see, gives a simple Lie algebra. So these are vector fields. I've got a bracket of vector fields that gives me a Lie algebra structure. And that's the so-called Witt algebra, which is, if you want, is a Virasoro algebra with zero central charge. Okay. So again, maybe in the background, maybe it's useful to backtrack a bit. So what do I want to do? So I want to have some sort of CFT which is defined on this path. And I've got like this topological thing which maybe you don't care about, but if you want to do things in an intrinsic local way, in the end you want to have something which actually is not going to depend on the global geometry. So in particular, it should be able to accommodate this kind of semi-exotic thing. So maybe I've got something like Ising model, which is defined in some way on that surface. And then maybe I've got like a bunch of mark points, and I want to look at correlations. And I want to look, for instance, at PPZ differential equations for such correlations. So in the end, that's what I want to do. And now I've got this kind of like geometric way to parameterize deformations. And okay, so again, so I've got this typical Laurent vector fields, and then to each such Laurent vector field, I can associate a deformation. And the first deformations are very easy to understand. So the first guy gives me just translation. So I'm going to take my disk, and then I'm going to slightly translate it. So what I'm doing is just translating the mark point. So the underlying complex structure is not going to change. I'm just going to displace a bit the mark point. So then the next guy is very important. So somehow the next guy actually changes the underlying complex structure of your Riemann surface. So what you do, so you have this vector field, which is, if you keep track, what you get is like basically Z inverse D over dZ. So now that's a vector field which cannot extend inside the disk. And that's because you cannot extend it inside the disk that it gives you a genuine deformation of the complex structure. So geometrically, it has very, this is often referred as a Schiffer variation. So what you do is you just take your scissors. So I take my scissors, I make a small cut in my surface like this. And then I'm going to open this cut like a lozenge, like that, and then I'm going to glue it back like an overslit. So this vertical slit, which I cut, I open it, glue it back as an horizontal slit, and that's you need to take slit of length like square root t, and then you glue it back, and that gives you a deformation which corresponds to the vector field dz over z. And then if you go on, you get the next guy is going to look like that. I'm going to make a small cut, which is this free leg star. So I'm going to cut, again with my scissors, I'm going to cut open these 3 leg stars. I'm going to blow it up into an hexagon, and then I'm going to glue it back in another 3 leg star, but I'm going to change the order in which I'm gluing. So these 2 guys become these 2 guys, and then they become these 2 guys, and vice versa. So, and then all the other higher order deformation are of that type. So you have this very simple geometric interpretation of what these deformations are doing. And now coming back to what we care about, so which are correlations in Cfts. So basically, if you're able to define a correlator, if you're able to take a scaling limit, so ideally what you want is have some sort of lattice approximation of your surface, and then have a model on it, and then you take scaling limit of correlations. So which I did not like that. So again, think a bit maybe slightly optimistically, you can do that for Ising, and then these are like spin or energy correlations. So now these are correlations which are defined somehow consistently, not only on your initial surface, but on all possible Riemann surfaces. So really what you have is a consistency theory for correlation which are defined simultaneously on all marked surfaces. And that's how you're going to extract information. So what you want, so now you can define this differential operator on your correlations. What you do is you take your correlator, and then you're going to start deforming your surface. For instance, you can imagine one of these 3 types of deformations, or actually hierarchy of deformations. And each of them, you take the derivative of your correlator along this 1 parameter family of surfaces. So you have this sigma t, which is a 1 parameter family of deformation of your initial surface. So now, clearly what you see, or if you think a bit, you see that you're going to get an issue because all these guys are kind of defined up to multiplicative constants. So each of these guys, when you normalize or regularize your scaling limit, you're going to divide by something to get a finite limit. So something like free energy, etc. So need to regularize all these guys, but now the issue is that it's not clear how you do it. I mean, you can do it for one guy. It's going to give you something which is well defined up to multiplicative constant. But when you have a bunch of different surfaces, you're going to do it for each surface. And for each surface, you're going to have a choice of multiplicative constant. And there's no consistent way to do that. And that's somehow crux of the matter, that there's no consistent way to choose this regularization consistently on all surfaces. Except for percolation, basically. So what you get is something which is indeterminate. So this procedure is indeterminate, but if you look at families of correlator, you get always the same indetermination. So this guy is going to change if I change my regularization. But if I change my regularization, I'm going to change it for all correlations. So you have something which is well-defined up to this global scalar factor. So what you get is not a representation of your algebra. So instead of having your vector fields, which operate nicely, they operate up to this ambiguity. And having a representation up to such an ambiguity is called a projective representation. So instead of mapping your Lie algebra to GLN, you map it to GLN modulo scalar matrices. So now that's kind of like very geometric and our intrinsic way to understand how this comes up is, okay, so what I'm saying is somehow if you manage to define your CFT in the limit, what you have is a representation, completely geometric representation of the Witt algebra, which is given by this process, but it's not the real representation, it's just a projective representation, because you have this ambiguity, and this ambiguity is really conformal anomaly. And this issue that you have is solved in the following way. So you have this standard classification result in representation theory is that if you have any projective representation of the Witt algebra, you can make it a true representation of some other algebra, which is the Virasoro algebra. So instead of having little LMs, I'm going to have like big LMs. I'm going to extend my algebra by adding one-dimensional line. So this C is a central element. So that's centrality. And you have this well-known Virasoro cocycle. So you have this like general theory telling you that, okay, so imagine that I managed to do, to take a scaling limit of CFT. If I manage to do this, morally, I've got a projective representation of the Witt algebra, and I know that any projective representation of the Witt algebra has to lift to a genuine representation of the Virasoro algebra for some central charge. So somehow that's a geometric way to think of central charge is you have this anomaly coming from this ambiguity when you renormalize, but that anomaly gives you exactly the central charge. So that's a way to understand it. So now I'm going to try to briefly explain this. So if you want to do it for, of course, like lattice model, it's going to be complicated because you need to be able to take limits of lattice models approximating basically all possible Riemann surfaces and so on. So that's a bit difficult. So what we do instead of is taking a model which is already in the continuum. Which is Liouville CFT. So this is slightly decorated GFF. So GFF Gaussian free field is just, or massless free field, if you want, is just a Gaussian theory. So something you can compute everything. So in a sense, it's empty. But it's also not summable on compact surfaces. So one way to make it at the same time non-trivial and also summable over compact surfaces is to add this Liouville term. So I'm going to write it as a path integral. So as a path integral, you have like the Gaussian path integral, and then you have a curvature term, which is going to make things consistent when you change your background metric. And then you have this proper Liouville term, so where mu is some like positive so-called cosmological constant, and then you have this multiplicative chaos, so slightly exotic, but somehow actually not so easy, not so hard to work with Gaussian multiplicative chaos. So now we have this well-defined CFT, so which have been studied a lot in recent times, especially following work by Kupianen, Rodon, Vargas. So these guys have also the benefit of having a lot of primary operators. So again, in Ising model, so primary operators, you expect to have only spin energy and the trivial one, which is identity. Whereas in CFT, you have a one parameter family of primary fields, which is defined naturally. So these are these vertex correlators again. So you just need to make sense of this, but actually it's not so difficult or so exotic. So okay, so in the interest of time, I'm going to skip that. So now, okay, so to summarize, so we have this, general idea of geometrically what should happen to CFTs if you take a limit, and geometrically how the VRSO algebra representation arises. And then we have a concrete model of LCFT, which we can define directly on any Riemann surface without sweating too much. And we can define these correlators as functions of a surface and a certain marking, and again without sweating too much. So we have this rich family of examples which are well defined and so on. And we can use this to somehow as a testing ground to check that all this machinery, which we expect to carry over for all CFTs, including coming from combinatorial models, is actually consistent and so on. So in particular, okay, so where the representation theory comes along, classically, going back to Belavin, Polyakov, and Zamoleshnikov, is through so-called null vector equations. So you have some special values of your weights. So that you have this family of primary fields, and then there are basically two special ones, or two simplest special ones, where the weight is one of these two guys, in which case, it's known, it's been verified again, in the case of the sphere by Kupianen, Rodon, Vargas, that you have this relation which, look abstract, but then if you write in coordinates, so your Teichmüller spaces are finite dimensional complex manifolds. So you can choose a system of coordinates. Once you choose a system of coordinates, this becomes differential equation. So there's a well-defined process from this kind of high-level conceptual relation to have concrete differential equations, which if you've seen it written, you recognize, you see them immediately. But that's a completely general procedure, which if you were starting in a more exotic situation, you at least notionally could write these equations. Of course, it becomes very complicated quite quickly. So we have very somehow simple-minded but idea, approach to do this, which is completely local. So maybe I don't want to get too much in detail, but we have this local construction of deformations where we pull out a disk and then glue it back with a deformation of the gluing. And then our basically approach to this equation is parallel to that and is well suited to this formalism, where we are going to pull out the disk and then basically condition the field inside and outside given the values of the disk, and then glue it back. And then when we make this deformation, it's going to change a bit the distribution of the disk on the boundary, but in a smooth way, and so on and so forth. So these are things you can sit down and analyze to arbitrary precision, because this is in the end this is all based on the Gaussian free field. So if you want to compute something, you can compute that, and you get this somehow abstract version or general version of the BPZ equation, which again in any geometry you can specialize and you get a concrete differential equation. So as I was mentioning, so these are the ones which are very well known BPZ equation on the sphere, and again, which were already proven directly, but with a global argument using implicitly uniformization, whereas in our case we don't have uniformization because we have multiple types of conformal structures. And this leads to this completely local geometric understanding of how these things go. So this looks pretty favorable. So so what we're working on now is something which is still a bit unclear, is higher order null vector equation. So in the representation theory, so this becomes very connected to the representation theory of the VRSO algebra, classification of Verma modules. So this corresponds to the existence of some special Verma modules which are degenerate at level 2, but there are special Verma modules which are degenerate at any level, so corresponding to these pairs of integers. So we have all these guys, and then you need to really understand something about about the representation theory and connect it to the geometry of your model. Okay, and this also, you can see if you're more familiar with that, it's closely related to vertex operator algebra and so. Okay, so maybe yeah, so maybe I'm going to stop there. Okay, thank you.
Thank you very much. Are there comments or questions? Okay, I have one. So can you elaborate a little bit more on the implications of your main equation? So given that, can you reproduce the results of Kupiainen and collaborators in a different way or in more general setting?
Yeah, so I mean, yeah, so for this we can reproduce, I guess. Yeah, so we can reproduce in, so it gives like a mechanical way to do it in any geometry. So, so I guess what we, if I just look at this, right? So we trust somehow like a rigorous version of argument that somehow, we're in the physics literature, but somehow, dealing with GMC and so on. So in the sphere, if I'm looking at, I can just parameterize by uniformization. So if you will, space of spheres with mark points, I can send one to infinity, and then I've got like finitely many coordinates. Everything is parameterized by finitely many coordinates. So somehow the way they use it implicitly use uniformization in some way. If you look already, okay, it's already in the torus, you can't do that because when you do this deformation, so what happens is if you do this, Schiffer variation, which is this thing where I pull out a vertical slit and then I glue it back by changing the deformation. Okay, so I do this this kind of deformation. It's going to change my modulus, so it's going to vary the modulus. And so then you kind of like need already in that case, which is some of the simplest case, or even in an annulus, if you will. In an annulus, you would have the same situation or the same issue. And then, again, so this like more complicated looking differential equation coming from where you have like theta functions coming up is really always the same somehow intrinsic canonical equation from which you derive in a mechanical way once you choose a system of coordinates on your Teichmüller space, you derive this type of equations, which becomes very quickly like very complicated. So on the one hand, you get more topology, but also the higher order picture, even in the case of the sphere, is not so clear. Because how you would do fusion, you would need estimate. It's a bit unclear. I mean, it's been verified, I guess, for the next one. You can still do that. But in general, you need somehow to understand, like for general RS, you need to understand. So another way to say it is kind of like procedure I explained. Basically, you generate, so there are this like canonical representation of the Verasol algebra, which you get from your model. So your model gives you correlations. These correlations give you highest weight representation of the Verasol algebra, which are defined in a completely geometric way. And now the question is, well, in representation theory, there's a classification of all these highest weight representation. Which are the ones you get, right? And for this, if I take like generic alpha, I get a generic representation. And if I take these two non-generic alpha, I get this special non-generic representation, which has a quotient, so which is reducible. But there are other values, special values of alpha for which you get like more complicated, or you're supposed to get more complicated representations. So actually, you're supposed to get like all the quotients of reducible verbal modules by maximal submodules. And so this is not very well understood, but that's actually what you get in LCFT.
Okay. There are a couple of questions online from Evelina Peltola. She asks, do you see SLE or CLE in this picture? And also, she asks, can you also analyze the semi-classical limit and find the geometric model for it?
Okay, so first question is no. So this is really not. So I mean, you know, there are some work by Cardi. I'm forgetting someone. And trying to do something like that for SLE or CLE, so that would be interesting to connect to that, but that's not really what we're doing. Because this guy, if you do it like locally, it becomes like very singular. So what we do is basically very simple. My idea is to look basically at the field on this circle, for instance, and if I write everything conditionally on what I see on this circle, I've got a smooth functional of this circle, which varies smoothly when I do this deformation. So if I back away a bit, then everything becomes smooth, whereas if you add this kind of like CL observable, then the singularity would be, you know, inside, and then that makes things, you know, complicated to work with. Again, if you're familiar with SLE, this looks like the basic thing you do in SLE, which is this, you start from a boundary component, and then you start going inside, and then you map it back to the flat. But here you have something which is a bit different, which is this, which I didn't explain. But you need to do that in every direction and extract the correct Fourier mode when you average over all possible directions in which you're making this deformation. So I've got, you know, I can do it at 45 degrees, where I take this guy and then you know, glue it back at over 45 degrees. So this is quite different from what you would see there. As to the other questions of semi-classical limit, yeah, I'm not sure about that, because you know, you'd get so what you would get is basically, you know, I guess, you know, divergence of the central charge. I'm not sure that's, I mean, I don't know that. I mean, maybe there is, but yeah, it might degenerate quite a bit. Yeah.
Okay. Okay. So I think we should proceed at this point. Thanks again to Julien for the nice talk. And we proceed with the next speaker, Yinon Spinka. Before it starts, a short introduction. Yinon Spinka obtained his PhD at Tel Aviv University under the supervision of Ron Peled, and later he moved to Canada, where he's now postdoc at the University of British Columbia. Yinon obtained several interesting results on phase transition in several combinatorial and statistical mechanics models, including POTS models, proper coloring, and loop ON models. And today he will present us his results on scaling behavior and decay of correlations in the near-critical planar Ising model. On independent sets in random subgraph of the hypercube. So please, Yinon, you can start.
Okay, thank you very much. Thanks for the introduction and for the invitation to speak here. So today I will talk about independent sets in random subgraphs of the hypercube. And this is going to touch on a few different topics, just to give you an idea of what will appear. Well, of course, we will see the independent sets, as you see in the title. But as many of you probably know, this is in statistical mechanics, this is just a special case of the hardcore model, where you have a fugacity parameter which allows you to sample a non-uniform independent set. And although everything I will talk about today works just as well for the hardcore model, just for simplicity, I'll stick to fugacity 1 and just talk about and just call these independent sets. But if you wish, you can have the hardcore model in mind. And we'll also see connections to the antiferromagnetic Ising model here. which will show up later in the talk. So in these types of models, there's various types of questions that people look at. One type of question is a counting question, so counting independent sets, or for the hardcore model or anti-ferromagnetic Ising model, this would be computing the partition function, which is a weighted counting problem. And then there's another type of aspect, which is structural information, for example, long-range order versus disorder, and so forth. Of course, both of these questions are very interesting and very closely related to one another. In the talk today, I'm mostly going to take the perspective of the counting side of the equation, but I will also address here and there the question of the structure. So most of the talk will be about counting and independence. But a lot of what I say is a bit more general than that. So the talk is based on joint work with Gail Cronenberg. All right, so let's begin with some quick definitions. So we're talking about independent sets in the hypercube. So let's begin with the hypercube. The hypercube is just 0, 1 to the d. This is the d-dimensional hypercube. Of course, it's hard to draw this in pictures, so I'll just kind of use the 2-dimensional lattice just as a sketch for the pictures, but I actually have the hypercube in mind. And I view this as a graph with nearest neighbor adjacencies, or if you wish, the Hamming graph. So two vertices are adjacent if they differ in exactly one coordinate. And an independent set is a subset of vertices which does not contain any two vertices which are adjacent to each other. Okay, so in this picture here on the right, for example, these two vertices, they're not adjacent, they're distant too, and you're not allowed to have, for example, this vertex here, or this one here. Okay, so let's denote by I Q of D the number of independents in QD. And as I said, our main focus today will be the problem of accurately computing this quantity asymptotically as the dimension tends to infinity. So this is the first problem that one may pose in this setting. And here the story begins. Well, let's first begin perhaps with some simple observations. So some trivial bounds. Well, the very trivial upper bound is just 2 to the 2 to the d, which is just all the subsets of the hypercube. So the hypercube contains 2 to the d many vertices, and these are all the subsets. Of course, that's an upper bound on the number of independent sets. And the lower bound is obtained simply just by considering sets which are contained in one side of the hypercube. So by side, I mean, this is a bipartite graph. We have the even side and the odd side, which consists of vertices whose sum of coordinates is even or odd. And these are the two bipartition classes of the hypercube. And if we just consider, so each one has size 2 to the d minus 1, and this just counts the number of subsets which are entirely contained in one of the sides, and there's a minus 1 because we are overcounting the empty set twice. So these are two very trivial bounds, and while it superficially they look very close to each other, this factor of half in the exponent, which the two bounds differ by, is actually very, very significant. So to try to better understand which of these two bounds is closer to the truth, let's try to slightly improve these bounds. So a non-trivial improvement, but something which follows from a general result of Kahn, who has a general upper bound for the number of independents that's in a regular bipartite graph. When applied to the hypercube, it gives this bound here, which is essentially 2 to the 2 to the d minus 1 times 1 plus 1 over b in the exponent. So that already tells us that we're slightly closer to the bound on the left in the trivial bound. We have this 2 to the d minus 1 times 1 plus little o of 1 plus 1 over d. However, this is still very far from the trivial lower bound, since in the trivial lower bound, if we write it in this form, it's 1 plus something exponentially small in d. And here we have a 1 over d. So this is still very far, and it's still not clear which of the two is closer. So there's still a big gap. Let's try to improve the lower bound. How can we improve the lower bound? Well, a naive way to do it is as follows. So instead of counting sets which are entirely contained in one side, let's count sets which are contained in one side except for k vertices, which are contained in the other side. So how many such sets do we have? Well, we need to choose those k vertices on the minority side, on the other side. We have this many ways to do it. And for any choice of k vertices, the neighborhood on the left-hand side, on the left side is at most d times k, since this is a deregular graph. And that excludes at most dk elements on the first side, which we can't take into our independent set. And that leaves us with another 2 to the 2 to the d minus 1 minus dk. Okay, we have this factor of 2 from the even-odd symmetry. And the only reason that this isn't an exact lower bound is just due to some overcounting, like the -1 we had here, but which is indeed negligible. So this is essentially a lower bound. And if you rearrange this, you see that this gives an additional factor of 2 square root e. Okay, so it improves this multiplicative factor of 2 to 2 square root e asymptotically. So that's a very minor improvement that we got from this computation. One additional thing I should mention here is that in order to get this 2 to the square root e, it's enough to consider bounded k, or more precisely, k's tending to infinity arbitrarily slowly. That already gives us this 2 to the 2 square root e. So in this sense, it's a naive bound. We're just counting independent sets which have a constant number of elements on one side, and on the other side, the majority of the set is there. So this is a very small improvement. And really the story begins with the following amazing result of Kurshanov and Sapojenko in '83, who showed that actually this naive lower bound is indeed the truth. So asymptotically, this is the number of independent sets in the hypercube. And what this means in a structural, from structural point of view, this means that if you choose a random independent set, uniformly at random, with high probability, the small side, so in one side, it's going to contain many vertices, and on the other side, it's going to contain a constant number of vertices. And actually, if you go back to what we did and work this out, you see that random variable is a Poisson half random variable. So that also gives you some structural information. Galvin later generalized this to the partition function of the hardcore model. As I said, these things work on the hardcore model as well, but I won't dwell on this too much. I won't tell you the exact results here. But very recently, Jensen and Perkins, using a cluster expansion, they were able to get very, very precise information on this little o of 1 term. So they essentially find they give a formula and an algorithm which allows to compute to arbitrary accuracy in 2 to the minus d, this series here. So this gives very, very precise information on these asymptotics, which is a very, very nice result. And finally, let me just mention that there are related results on tori and on the ZD, both structural and counting results by a number of people. But this is not something I will focus on today. Okay, so the talk today is going to be about random subgraphs of the hypercube. So specifically, we're going to look at QDP, which is a random subgraph of the hypercube obtained by keeping each edge independently with probability p, or in other words, removing each edge independently with probability 1 minus p. And our problem of interest is going to be to understand the number of independent sets in this random subgraph as d goes to infinity for various values of p. So here, if we look at such a independent set, since we have some edges removed, these edges in black shown here in black, it might happen that two vertices which are originally adjacent are in our independent sets because this is an independent set in a subgraph of the hypercube. Okay, so we get many more options, many more possibilities now. And just to mention before we start talking about this problem, these random subgraphs have two kind of interesting points. So one is around p equals a half, and this is the threshold for various global graph properties, such as the existence of isolated vertices, connectivity, perfect matchings. Recently, this was shown to be the threshold for Hamiltonicity. And another important threshold occurs around 1 over d, which is the percolation threshold, or in other words, where a giant component appears. And this has been the subject of much study as well. So that's just to give you some idea about these random subgraphs and the various people who have been studying these. And what we're going to do is study the number of independent sets in this random subgraph. So here's our main theorem. So for p's which are not too small, at least a constant log d over d to the 1/3. Okay, so p's are allowed to tend to 0 polynomially fast, like log d over d to the 1/3. We compute the expected number of independent sets in this random subgraph. And we have this formula here. And you see that the p comes in the expression in the exponent, and we have the 1 plus a little of 1 in the exponent. However, just as previously we saw with the Jensen-Perkins result, here too, we can get much finer information on this little o of 1. And as we'll see later, this is also using a cluster expansion technique. And so I'll just give the next term here. So the next term is some function of p, which is explicit, but I won't write down here, times this d to the d minus 1 minus a quarter. And we have this 1 minus p over 2 to the power 2d. And the next terms are going to be powers of this 1 minus p over 2, so to the 3d and to the 4d, and henceforth. So again, we give a formula and an algorithm that allows you to compute this to arbitrary accuracy. However, we know not only how to compute the expectation, which is the first moment, we know how to compute higher moments as well. And here I'll just give the basic form. I won't. So here too, we can give more information on this little o of 1 term, but this becomes a bit more complicated to write down, and I won't go into this here. But I just write down here the very basic form. So just to give you an idea of what type of to see explicitly what type of things this gives, let's just look at p equals a half, and here's for example what it gives at p equals a half. Okay, so it actually gives us the asymptotics, 1 plus little o of 1, not in the exponent, but down in the down below. So it gives the asymptotics just because at some point these 3 dots are going to be they're going to be a little o of 1, and then you can pull that out of the exponent. So once you go far enough in this series, you actually obtain the asymptotics of the expectation and the variance, for example. And if you go down even further, you can also get more information on the little o of 1. So this is just an example. Some corollaries of these types of results. So one result we have is about a distributional limit. So for p's tending to 1, not too fast, and I won't write down exactly the technical condition. What we show is that the number of independent sets is actually normally distributed once you subtract the expectation divided by the standard deviation. And this convergence is both in distribution and in fact in moments, in all moments as well. For p's which are at least 2/3, we can show that this quantity here is tight on the one hand, and on the other hand does not converge to 0. Okay, so this shows some type of concentration. And to plug this in more explicit values of the expectation and variance from the previous theorem, this can be written in this form. So we know that with high probability, the number of independent sets has this form, with a 1 plus something of the order 2 to the minus 3p over 2 to the power d over 2. And I'm slightly being vague about what this theta here means. I don't want to get into this too much, but maybe just quickly say that this is with high probability a big O, but it's a big omega only with positive probability. And one thing to note here, this is a very interesting thing, I think, that it seems that at the point 2/3, something here is happening, because if you look at this expression here at 2/3, this is order 1. So actually this is saying that at 2/3, there's no concentration. The number of independent sets is not a concentrated value, whereas for p larger than 2/3 it is. And we don't actually know what happens for smaller p, but we expect that it's not concentrated either. And this is interesting. Perhaps there's this 2/3 is another point of interest in the hypercube. Okay, so I think I have about 10 minutes left. We started, I think, 10 minutes late. So perhaps in the remaining time, I'll just give you a bit of ideas about the tools and ideas of proof. So in a very high level, the first step that we will use is some connection to a positive temperature model. And what do I mean by this? So one of the models that appears here is the antiferromagnetic Ising model, which I mentioned on the first slide. So this is a model where the interactions are they're not hard constraints, right? They're soft interactions. And this is what I mean by a positive temperature model. Okay, so in the independent set model, two vertices are simply not allowed to be adjacent to each other. That, if you wish, has infinite energy. Whereas in positive temperature models, I mean that everything is possible, but it comes with some energetic penalty. So we'll see that relation. A second tool that comes into play is a cluster expansion for a certain polymer model, which appears in this setting. This was used by Jensen and Perkins as well in their setting for independent sets on the hypercube. We'll also use some coarse graining or approximation scheme for contours. These types of ideas go all the way back to the result of Khrushchev and Sapushenko, and they were used by Galvin as well, and many others in this area. And finally, we're going to use some entropy methods and a comparison. We're going to compare the independent set model on the hypercube to the independent set model on a bipartite graph, complete bipartite graph, KDD. And this will allow us to obtain information on the hypercube by understanding the much simpler situation of the model on the complete bipartite graph. Okay, so let's dive into the first point here. So I think I'll mostly just talk about the first and second points. I don't think I'll go into the second 2 points for lack of time. Yeah, but the first 2 points will already give the basic ideas of what is what's going on here. Okay, so let me do this in handwriting here. So instead of doing the full derivation here, which is actually not at all hard to do, I thought I'd just give you some indications of why such a connection is there. So first of all, heuristically, if you think about first sampling the random subgraph and then sampling a uniform independent set on the random subgraph, so we have 2 steps of randomness. But if you kind of think about just the marginal distribution on the final set that you get, on the subset of the hypercube that you sample at the end, as we saw in the picture I showed a while ago, 2 vertices which are adjacent on the hypercube might end up being in that set, just because the edge in between them might have been deleted in the first step, where in the random subgraph. So you might kind of heuristically imagine that in order for 2 adjacent vertices to both be in the independent, to both be in the set, it kind of comes at a cost, because it requires that the edge be deleted in the first step of randomness. And that it almost has the feeling as if this is exactly the antiferromagnetic Ising model, but it's not exactly that. But it is very much related, and this is this connection that I'm telling you about here. So let's write some stuff down. So the first step of randomness, what we do is we sample a random subgraph, a random subgraph of the hypercube, and the probability we get a specific graph G. So this is P to the number of open edges in G, 1 minus P to the number of closed edges in G. Because this is just independent. And then the probability of a specific subset that we get at the end of the hypercube, given the first step of randomness, given the graph that we have, well, this is just a uniform independent set. So this is the indicator that I is independent in G, divided by the number of independent sets in G. So if we look at the marginal, distribution on the set that we get at the end, this is proportional to, well, we need to sum over all possible G's and write down the product of these probabilities. So actually the indicator that I is an independent set, that just means we're summing over all graphs such that I is independent in G. And once we sum over these graphs, we have here P to the open edges, 1 minus P to the closed edges, and 1 over I of G. All right, but this 1 over I of G is a bit annoying, but what happens if we define a new, so if let's call this measure mu, and if we define a new measure nu by tilting it according to the number of independent sets, and normalizing it so that it's a probability distribution. Okay, in other words, this Z here is nothing other but the expectation under mu of the number of independent sets, which, remember, this is a quantity we wanted to compute. This was in the first theorem. So if we do this, we see that the probability of a set I under nu, well, this 1 over I of G now cancels out, and in the sum, the only thing that's fixed is that the edges inside I, so anytime there's an edge of the hypercube between 2 vertices of I, that edge must be closed in G. So what we get is that this is proportional, or yes, this is proportional to 1 minus p with the power, the number of edges in I. Okay, which let me write as e to the minus beta times e to the I. So here p, 1 minus p is e to the minus beta. Okay, and writing it like this, what we see is that actually z is the sum over all I of e to the minus beta ei. Okay, and this is the partition function of a positive temperature model. The beta is our inverse temperature. If beta was infinity, this would exactly be the number of independent sets in G. But if beta is finite, this is computed. This is a weighted counting where we're allowing any possible I, but giving a penalty, an energetic penalty every time we have two adjacent elements. And actually, this is exactly the antiferromagnetic Ising at inverse temperature beta over 4 and magnetic field h d over 4. So this over 4 comes from the different normalizations here and in the Ising. Okay, so this is this relation I wanted to tell you to the Ising model, to the positive temperature model. And actually, there's a similar type of relation for the moments as well. So the kth moment can be written as a partition function, let me call it ZK, of an antiferromagnetic Ising type model, but where instead of one component, there's K components. There's kind of K superimposed Ising models, one on top of another, but they interact with each other in the following manner. So we sum over I1 up to IK. These are the K Ising models. But we have here e to the minus beta times ei1 union up to eik. And what this means is that, what this means is that actually the energy across a bond is, well, if one of the copies, if one of the I1, I2, or I3 is frustrated, if one of them has two vertices occupied, then you have a positive energy on that bond, but having more copies frustrated doesn't increase the energy. So the energy is just, the bond can be frustrated at most once. This is what this means. That's the interaction between the different copies. If there was a sum here instead of a union, the sum of the sizes, then these would just simply be independent Ising models. But because there's a union, these interact with each other. Okay, so I'm out of time, so maybe I'll just mention for the polymer model that what one does is one sees that one's trying to aim that to a situation where most of one of the side is occupied and the other side kind of is very dilute, and one wants to write these dilute deviations on the right-hand side as to view these as polymers with a weight, which kind of gives you the deviation from this basic ground state, where the ground state is where everything is only occupied on the left-hand side and nothing occupied on the right-hand side, and you obtain a polymer model where you have these where the right-hand side, which is the minority side, kind of splits into the connected components, which give the polymers. And this gives us a polymer model, which one can then apply the cluster expansion techniques to. And these last 2 points that I mentioned are there in order to verify the convergence of the cluster expansion. So the coarse graining and the entropy methods, those come in order to show that the cluster expansion indeed converges, so that one can obtain a converging series and get the results that I was mentioning earlier. Okay, so I hope this gives you some ideas, and yeah, and I'd be happy to answer any questions. Thank you very much.
Thank you. Comments, questions? Okay, I have one. So can you discuss implications of these results for the phase diagram of this the specific model you studied, and possibly more general hardcore models in high dimensions?
Yes, sure. So if we actually look at the independent sets on the random hypercube, we're still missing some information. So there's two steps of randomness. So there's kind of quenched questions and annealed questions. And we don't understand these exactly, but too well. But if you look at this related model, the positive temperature model, so I'm interpreting your question slightly differently. We do understand the phase diagram for this gives some information about the phase diagram of the antiferromagnetic Ising model, and it tells you something about what happens near magnetic field roughly D. So if you have an antiferromagnetic Ising model, meaning that pluses want to be next to minuses, but then you amp up the magnetic field so that you want a lot of pluses, and you tweak it exactly around D. There's a threshold around there, and this gives some fine information on the threshold around that point.
Maybe just so, does this have any connections with the random packing problems that people studied in high dimensions? So also with the replica trick. I mean, for instance, people around Parisi.
Not that I know of. I would be a bit surprised if yes, but that's a good thing to investigate. Yeah.
Okay, I don't see online questions. Are there any other questions from the audience here? Okay, if not, thanks Yinon again. And well, this was the last talk of the sessions in equilibrium statistical mechanics. So thanks also to all the speakers of these sessions, and thanks to the audience here in site and online. And I don't know if Ivan Velenik is connected. I mean, he's certainly connected. I don't know if he wants also to hi, to say hello. And no, we cannot hear you.
No?
Yeah, now yes.
Hear me? Okay, good. So yeah, I would also like just to thank all our speakers this week for their very enjoyable and instructive talks. And I hope to see you in person soon. And you too, Alessandro. And thanks for sharing all these sessions.
Okay. Yeah, thanks also to you. Thanks to everybody here. I hope you also enjoyed these talks. And well, good continuation.